Good afternoon. This is Andy Schweitzer in a short video on two things. First thing is going to be the flame test, and we will also be looking into some of the theory behind light production. So a little bit of pre-lab, and then we'll be looking at some of the actual content of what's going on and what you should be focusing on for your particular lab conclusion. Now, so light production, people have known for a long time that if you take something and you put that something under the energy-wise and you heat it, let's say with a Bunsen burner, then this thing's gonna glow or give off some amount of light. And it's been theorized that what happens is you have an atom. The atom has multiple energy levels. It's got a nucleus that if you take a substance, electrons are sitting in here. Now, if you heat this thing, it takes or give it energy. There's a lot of ways to give this thing energy, but you apply energy, whether through heat, you actually whack it with electrons of various voltages. But either way, you apply energy to this thing, just like you're applying energy with the Bunsen burner here. And it jumps from what we call the ground state and then shoots up to what's commonly referred to as an excited state. At that point, the electron can, when given time, it has extra energy here, it can drop down back to its low ground state. But in order to do that, it needs to release the energy that it currently had, because these are energy levels, and to get to a lower energy level, it needs to have a lower energy. So that energy, seeing as energy is conserved, has to be released, and it gets released in the form of a photon. Now, a few things about this ground state and excited state. Every single electron has what we call quantum numbers. Okay, so let's just say, for example, that this is, I'm going to put another electron here. So let's just say it's got 4 electrons, 4 protons. So this atom is beryllium. Okay, so this electron right here, whenever we do an electron configuration, we do it in what we call the ground state. So we're assuming that the electrons are in the lowest possible states they are. So this would be for beryllium 1s2, 2s2. And we'd say that this particular electron, this guy right here, could have quantum numbers of 2. It's in the s orbital, which is a 0. It has 1 suborbital, which is 0, and it's to say plus 1/2 for the spin component. So in this case, this is the electron configuration for electrons in the ground state. As you warm them, obviously it can get shut up into newer, unused, higher excited state. So I could write this, let's say, like this: beryllium Be 1s2, 2s1, let's go 2p1. Now that shows one electron is sort of excited up into a higher energy state. Either way, we just generally write it in its ground state. This is 99% of the time is what we do. Again, how is light produced? It's caused by electrons that are energized up to higher excited state. When they fall back down is when they must de-energize and then give out a photon of light to allow it to de-energize back to a lower energy level. Okay, so what is this light? Okay, well, the light that comes off this photon is retrospective or due to the difference in energy from n, let's say, equals 2, n equals 1. So the difference in energy between these two energy levels is the energy of the photon. So you should be aware that as I put energy into this thing to excite it from the ground state to the excited state, this photon cannot be, energy of the photon cannot exceed the energy with which you put in here. You hit this with some energy, and assuming all of it was absorbed, it got kicked up to a higher energy level and then it came back down. So in our lab, we're going to be heating something with Bunsen burners. Now, so a Bunsen burner, okay, my little Bunsen burner, got a little flame here. Not a very good Bunsen burner, but we're going to heat something with this Bunsen burner. So this is the amount of energy that we're putting into it. So the light that is given off, okay, the photons, really can't have any more energy than what the Bunsen burner is providing. So if I want a higher energy photon, I'm going to have to put more energy in to either ram it up higher or to do other things. Either way, I'm not going to be able to get more energy out than I put in. Okay, so this photon, what's important about this photon is it is reflective of the electron structure. So photon, okay, reflects electron structure. We often think of it as a fingerprint, or a way to identify the actual the actual chemical. Nowadays we have lots of sophisticated ways to identify things, but years ago this might have been a main tool for chemists. Now the actual photon is often referred to as a wave. Okay, and this wave, again, is it a particle? Is it like I'm showing here as a little particle coming off, or is it a wave? Scientists will argue about that, but either way, this wave might look something like this, okay, or it could have a smaller wavelength and go faster, 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 and eventually have like this. So this is your typical wave, and this is called the wavelength, the distance between the two crests, or any real point adjacent to the next point. So the middle to the middle would be the wavelength as well. Actually, this one should be the other side right here. We call this lambda. As you go down, okay, this would be an example of right here of a high energy. So energy is increasing, and this would be relatively low energy, whereas this would be a high energy wave. So your spectrum of energy as far as light is concerned, there's a very small section called visible that we can actually see, and some higher energy versions of light might be gamma, there we go, gamma, G-A-M-M-A, X-rays, more dangerous because they have more energy, and with more energy you could do more things, good and or bad, I guess. We could have ultra violet, all right, infrared, and then we have like radio. I think microwave would be in here too. All right, so all these different, this is actually referred to as the light spectrum, okay, the electromagnetic spectrum. Light's often referred to as an electromagnetic wave. All right, so let's talk about our lab procedure. First of all, procedure-wise, the main objective is to determine an unknown chemical via flame test. Do not lose sight of what is going on as far as what we're trying to figure out. All right, so the basic procedures we have is we'll basically have two containers on your lab. We have a beaker here which has a chemical in it. We have one that has an acid and one that has, the other chemical might look a little different or it may not. Depends on how it's set up. But two chemicals. All right. This one, let's say, has strontium nitrate. Just example. Okay. You take your little nichrome wire. Okay, it's got a loop on it which allows to hopefully grab onto a little more liquid. And then we have our Bunsen burner. With its wonderful little flame on there. Okay. You place your stick into the acid, and that is a cleaner. Right? Then place it into the flame to burn off the acid. Then put your stick into the liquid. You might hear a little sizzling, which is fine because it's hot. Then place it back once again into the flame, and at that point observe what color it is. Look what color it is. All right, this is my eyeball. All right. So for this, that's basically it. Then it goes back into the acid once again to clean, and then flame, then chemical to be tested. Generally the metals are the ones that tend to produce the best colors here at low energies. So you'd want to have a table. You'll find on my jars, at least, I have the metals circled. And the metals are the ones that are going to produce the best light in the visible spectrum that we can see at low energies. So you might put substance here and then color that is here, and then maybe you want to have another box that says unknown, what you found the unknown to be based on the colors. Now, again, for the lab conclusion, you could say, oh, you know, like the colors matched, I'm done. Well, you need to go through and say, well, if the colors matched, I understood it, but the reason why the color is important is because of all of this stuff right here, all of the idea. And in this case, a picture might be worth a million words, but you'll need to explain why, just because the colors matched, it is a valid to say these are the unknowns. And I will say, at least at this point, there's more than one unknown mixed together in my procedure. So you might have a couple unknowns. You'll see a couple different colors. So procedure-wise, make sure you have that set up, and then you can get your lab completed. Thank you very much.